The Internet's ideal is an infinitely connected web where readers jump from node to node. A physical book, by contrast, forces a rigid, linear sequence. When hypertext first emerged, designers believed breaking that linearity would liberate users. The assumption was that allowing people to freely traverse rich semantic networks would automatically lead to a deeper understanding of the material. Decades of usability research have revealed a persistent paradox. Giving users complete nonlinear freedom consistently triggers spatial disorientation. Users frequently lose track of their position within a site's hierarchy. This disorientation directly degrades their ability to comprehend and retain the complex information they are trying to read. Designing an interface based on the technical capabilities of the web, rather than human cognitive limits, actively damages information retrieval. Navigating any digital space relies heavily on the visuospatial component of human working memory. This animated chart illustrates cognitive compatibility, the match between a digital system's features and a user's finite visuospatial limits. When a site requires complex navigation, heavy conceptual blocks of orientation drop into that capacity, severely reducing the remaining space for actual comprehension. When cognitive compatibility fails, the user's working memory is consumed by trying to figure out where they are in the digital environment, rather than processing what they are reading. By deconstructing the empirical data behind standard UI components, we can trace exactly how human cognition demands explicit, hierarchical structures over dense, nonlinear networks. Effective information architecture requires ruthlessly guarding the user's working memory at every step. A common assumption in link labeling is that contextually embedded hyperlinks, like the ones used throughout Wikipedia articles, are the ideal way to guide users. A 2001 study tested this. Users read content via embedded links on the left or an explicit side menu on the right. While subjective feedback favored embedded links, empirical data contradicted this. There was zero advantage in search accuracy or speed compared to the side menu. Subsequent research by Kahn and Locatis tested link density. They found that doubling the number of embedded links on a single page actually decreased the user's search accuracy. Every additional embedded choice within a paragraph forces a micro-decision. Users either have to stop reading to evaluate the link or extract the surrounding prose to parse its relevance, multiplying the opportunity for a cognitive mistake. Subjective user preference does not equal cognitive efficiency. Highly contextual links often act as cognitive friction rather than reliable navigation aids. A specific psychological mechanism explains why jumping through these embedded links destroys comprehension. Researcher Peter Fultz identified the importance of local coherence, the contiguous thread a reader builds when moving linearly from one sentence to the next. Users approach complex text aiming to build a singular, uninterrupted route to form a solid macrostructure. Suddenly jumping to a new page shatters that linear path. Clicking an embedded hyperlink causes local coherence breakdowns, forcing the brain to process an entirely new environment. The data shows that users who resist clicking away and instead maintain a linear route respectful of the text's original macrostructure recall significantly more information from the document. Careless networking of text forces the brain to constantly rebuild its mental model. Seamless reading requires highly restricted, linear link architecture to keep that model intact. The same cognitive limitations dictate global site navigation. The primary architectural challenge for any site menu is optimizing the depth-breadth ratio. A study by Rouet tested a deep menu against a broad menu. Navigating the deep menu's 4 levels forces a heavy spatial cognitive load. Conversely, the broad categorized menu, exposing up to 42 grouped items simultaneously, yielded the highest task success rates. Researchers measured task difficulty using a metric called lookbacks, calculating how often a user had to reread their original goal prompt while navigating through the site. Broad categorized menus resulted in significantly fewer lookbacks. Users navigating flat, wide structures required drastically less mental effort to hold their objective in mind. Burying information under multiple clicks causes disorientation. Exposing wide, clearly categorized arrays up front respects working memory and accelerates retrieval. To combat disorientation, designers often provide graphical content maps that chart the entire architecture of a website. The success or failure of these visual navigation aids hinges on a single hidden variable, the user's prior domain knowledge. A study mapped a subject using an alphabetical index, a hierarchical map, and a semantic network. The semantic network accurately maps complex relationships, but this dense web hindered novice comprehension. In contrast, novices scored significantly higher using the simplified, rigid hierarchical map. Complex semantic maps force novices to spend vital cognitive energy decoding the implicit relationships drawn by the designer. Hierarchical maps act as an explicit structural cue, performing the necessary categorization work on behalf of the user. Designing for novices requires hiding the true complexity of a network. You must spoon-feed them a rigid, top-down hierarchy to allow their internal situation model to form. Designing for cognitive compatibility means assembling an interface that actively protects visuospatial memory at every layer of interaction. We assemble the ideal interface based on empirical data. A persistent left panel provides a broad, categorized menu. The main text remains entirely linear. Embedded links migrate to a right-hand contextual box, preserving coherence. Finally, a top-down visual map explicitly outlines the macro structure. This specific, data-backed wireframe minimizes choices, prevents coherence breaks, and offloads structural tracking. It leaves the user's brain fully dedicated to reading comprehension. This reveals the ultimate irony of digital information architecture. Despite the limitless, non-linear potential of hypertext, the strict prerequisites for digital comprehension are identical to traditional print reading. Both formats demand explicit organizers, clear signaling, and rigid top-level thematic structures to guide the reader through complex ideas. True innovation in interface design does not come from flaunting technological complexity. It comes from recognizing and mastering the timeless, biological limits of human cognition.